3, 2, 1. Engine full power and liftoff.
A spacecraft leaves Earth, points to the nearest star, and pushes forward through the darkness of space. At first, acceleration is timid. Then it becomes steady. Hours slip into days. Days pile up into decades. And even after all that effort, the journey would barely be past the prologue. We're not talking about a hop to Mars or a landing on Titan. The topic here is different, truly crossing the limits of our solar system and facing the emptiness between the stars. So why, with all human ingenuity, haven't we taken that step? What makes leaving home in the cosmic sense so hard, even with rockets and probes that already feel like science fiction? Today, the plan is to face the obstacles head-on, distances that defy imagination, an energy bill we don't know how to pay, biological limits that follow us everywhere, and a silent but absolute adversary, time. Since the late 1950s, the species that learned to dream by looking up has started to lay hands on the sky. In 1957, a small metallic transmitter, Sputnik, kicked off the space age. A few years later, Yuri Gagarin showed that a human could orbit the planet and come back to tell the story. In 1969, Neil Armstrong and Buzz Aldrin made lunar dust record the first human footprints on another world in an Apollo mission that became the symbol of an entire decade. From there, we spread robots across Mars, parked orbiters around Jupiter and Saturn, and launched persistent explorers like Voyagers 1 and 2, which are moving beyond the sun's sphere of influence. Voyager 1, launched in 1977, is now more than 24 billion kilometers from home. Impressive, of course. But when the goal is reaching another star, that monumental feat shrinks. It's like taking a step outside your house when the destination is thousands of kilometers away on foot. Despite everything we've done, we've only turned a few pages of the cosmic book, and it's much thicker than we'd like. The root of the problem has a first and last name: interstellar distance. Our own backyard is already enormous. The average distance between Earth and the Sun, about 150 million kilometers, even has its own nickname, an astronomical unit. Now try scaling that up. Voyager 1 took more than 4 decades to cross the heliopause, the boundary where the solar wind gives way to interstellar space. And even so, it hasn't come close to any star. The nearest neighbor, Proxima Centauri, is part of the Alpha Centauri system and sits 4.2 light-years away, approximately 9.4 trillion kilometers. Multiply that by 4 and a bit more, and you start to feel the weight of the problem. If a commercial airliner, the kind that crosses oceans, could follow that route directly, the trip would take on the order of 5 million years. And Voyager 1 itself, cutting through space at about 61,000 kilometers per hour, would need more than 70,000 years to get there. This isn't hyperbole. It's the same old math applied to the most uncomfortable scales we've ever faced. Given that, the conclusion seems obvious. We'd need to travel much, much faster. And there we hit another wall: energy. The rocket engines we know, powered by chemistry, are great for what we've mastered: escaping Earth's gravity, maneuvering between planets, landing probes. But when the ambition is interstellar, they exact an impractical price. The farther we want to go, the more propellant we need to carry, and the more propellant on board, the heavier the vehicle becomes, demanding even more propellant, an escalating cycle. Even if we stacked stage upon stage, the energy efficiency of this method barely scratches 1% of the speed of light. Alternatives like ion propulsion use particles accelerated by electric fields to push a spacecraft gently over long periods. It works beautifully for missions that demand patience and thrift, but the thrust is so small that reaching truly meaningful fractions of light speed remains a distant dream. Of course, human imagination doesn't stop at today's methods. Bolder plans live on paper and in laboratories. Nuclear fusion propulsion, for instance, tries to bottle the same kind of reaction that powers the sun to produce thrust. In theory, that would let a spacecraft accelerate to a respectable fraction of light speed. In practice, we're still struggling to master fusion in a controlled, efficient way here on Earth. And turning such a reactor into something compact, safe, and reliable for a spacecraft, that would demand decades of progress in engineering, materials, and plasma control. Another exciting idea is sails, reflective surfaces pushed by the pressure of light. They can be driven by photons from the sun, or more aggressively, by powerful lasers fired from Earth. The Breakthrough Starshot project follows exactly this path. Launch microprobes and accelerate them with high-power beams to something like 20% of the speed of light. At that pace, Proxima Centauri would be 20 years away. Sounds perfect until the caveats appear, keeping a narrow beam locked over absurd distances, ensuring materials survive the bombardment, and perhaps the hairiest challenge, figuring out how to slow the probe down on arrival so it doesn't just fly past without being able to observe anything calmly. Even setting propulsion aside, there's another tricky question. Where will the energy come from to keep everything running during the trip? The farther from the sun, the less light helps. Solar energy, so helpful at Mars and still useful at Jupiter, fades until it becomes irrelevant after a few dozen astronomical units. The fallback then is nuclear sources. That's how it worked with the Voyagers and with the Cassini mission. Radioisotope thermoelectric generators, the famous RTGs, turn the heat from radioactive materials into stable electricity. They're robust and last a long time, but not forever. They deliver little power, and in the end, the battery runs down in a few decades. To keep systems alive for centuries, or even millennia, we'd need something more durable, efficient, and safe than anything we have ready today. Sure, we could dodge some of these dilemmas if we gave up on human passengers, but if the idea includes people on board, the list of problems grows. Our bodies evolved for Earth's gravity, filtered by its atmosphere, and protected by its magnetic field. In deep space, the story is different. Ever-present cosmic radiation raises the risk of mutations, neurological damage, and cancer. The absence of gravity erodes bone and withers muscle. Astronauts on long missions have to exercise daily with specialized equipment just to slow the loss. Now imagine maintaining a healthy body for decades, and we haven't even talked about the mind. Isolation, repetition, the emotional distance from Earth, all of it takes a toll. Long-duration confinement experiments like Mars 500 showed how mental health is one of the toughest bottlenecks in extended missions. To top it off, interstellar-scale communication is absurdly difficult. A signal sent from Proxima Centauri would take more than 4 years to reach us, and the reply, another 4. Real-time support? Forget it. Faced with this scenario, proposals arise that are as ambitious as they are controversial. So-called generation ships imagine self-sufficient habitats, true sealed worlds crossing the vacuum, where several generations would be born, live, and die until, one day, the descendants of the first crew arrived at the destination. Logistically, it can make sense. Ethically, it opens wounds. Those born on board didn't choose the mission, yet they spend their entire lives serving a goal decided by their ancestors. How do you guarantee freedom, culture, education, health, and purpose in a completely artificial environment, isolated for decades or centuries? Another line of thought tries to skip the social drama via the long sleep, states of hibernation or cryogenic preservation that would keep crew members dormant until the end of the journey. Science fiction loves the image. Pods in neat rows, blue lights, silence. Reality isn't even close. We don't know how to preserve a human organism alive and intact for that long without irreversible damage, and then switch it back on as if nothing happened. And even if we solved the engineering, biology, and psychology, the final judge would remain time. Einstein's relativity taught us that time is no universal metronome. As we approach the speed of light, the clock aboard runs slower relative to those who stayed behind. In practical terms, at 90% of light speed, the crew would age more slowly than people on Earth. On a trip like that, the years inside the ship could fit on your fingers, while decades outside stretched into centuries. It's a kind of cosmic trick. The travelers beat subjective time but lose their bond with the world they left. On returning, if they returned, nothing they loved would be recognizable. Friends and family would be gone. Languages and cultures would have changed. Humanity itself would be different. A mission like this stops being merely logistical and becomes a final farewell to the present, a cultural break. And that erases the fantasy of an interstellar civilization like the series we love, with planets trading resources and sending weekly messages. Physics, at least as we understand it today, doesn't support that 24-hour galactic coffee shop. This stark reading of the cosmos may even offer a possible answer to the famous Fermi paradox. If the universe is so vast and rich with stars and planets, where is everybody? Maybe everybody is trapped, like us, in their home neighborhoods. The distances are too great, the energy, biological, and temporal barriers too severe. Even much older civilizations may have faced the same wall and concluded that crossing it costs more than any society would be willing to pay. It's not that intelligent life isn't out there, it's that each one, circled by its own limits, can't bridge the abyss between oases. Where gardeners in backyards separated by deserts no lifetime's effort can cross. But none of these realizations should invite discouragement. After all, is the physics we know today the final draft of the story? Or are there still hidden edges, poorly understood phenomena, combinations of ideas capable of opening small shortcuts where we now see only walls? The past is full of impossibles that became routine. Flying was a myth, crossing oceans in hours, madness, talking in real time with someone on the other side of the planet, magic. Of course, comparing airplanes to interstellar ships is bold. The orders of magnitude are different. Even so, the attitude that got us here was to observe, test, fail, learn. Maybe somewhere along the way, there's a way to concentrate energy more efficiently. Maybe a material will emerge that withstands accelerations and heating we currently can't imagine. Maybe we'll discover biological techniques to protect body and mind in zero gravity. Maybe a mission architecture that combines many maybes will shave centuries down to decades and turn far into just hard. Until that maybe takes shape, there's a concrete, valuable path. Keep pushing the frontier of what's possible, even if only within our system. Every robot landed on Mars, every comet flyby, every image wrung from Europa or Enceladus, every map made of Titan, every measurement of the solar wind teaches us something. Added together, these lessons build real steps. Our generation may not live to witness a laser sail streaking through space toward another star, but it is our generation that can consolidate technologies, validate concepts, and hone strategies that make such audacity less unlikely for those who come after. Today's impossible, by definition, only stops being impossible when we start building its foundation. So I'll turn the question back to you. Do you believe we'll one day be able to leave the solar system aboard a crewed ship? Do you think some combination of science, engineering, and stubbornness will carry us beyond the sun's influence toward another star? Tell us in the comments which scenario seems most plausible to you. Generation ships, laser sail probes, hibernation, fusion, or some other path we haven't even imagined yet. If this video helped you grasp the scale of the challenge and still left you eager to keep exploring, hit the like button, share it with someone who loves space, and of course, subscribe to the channel. Thanks for watching, and see you in the next video.